Hi everyone. So in this video we'll talk about one of the most important and fundamental topic in the algorithms in the data structure, which is complexity. As we know, the most important question is every kind of the solution in the algorithms. How fast does this algorithm run and how much memory does it use? Moreover, we will learn about what exactly big O notation and how constant time, like the logarithmic time, square root time, linear, quadratic, exponential, factorial time works. The main difference between them, what kind of problem what kind of the problems each one use it for, real LeetCode problems for each complexity, and how to analyze problems, mathematical and logical solutions we will see. So our first topic is big O notation. So big O describes how the running time of algorithm changes as input size grows. If it draw its graph as a simple linear graph, it looks like this. We have this horizontal line, which is time, complexity we can see, and input size we can compare. And its line looks like this shaped. This is a ON we can see, and this line we can call linear, or linear growth we can see. Let's look at a real life example. Imagine we have several bags. Line it up 1, 2, 3 something till some kind of the number of the bag. So, and only one of them contains some ticket in the bag. If we start search and find it in the first bag, we don't need to check others. Like for example, let's imagine we have one ticket in the first bag. We don't have to search other bags because this is only one unique bag. But if the ticket is in the last bag, what should we do? We have to check every bag before the finding it. If the bags are 10, if there's a 10 bags, we perform 10 iterations or 10 operations. First check, no, second, third, and etc. of 10 still. If 1,000 bags, we perform 1,000 iterations and so on. That is why it's called linear growth. So in real problem solving solution exercises, we usually apply this concept through algorithm analysis as well, using two important concepts, as we said, which is firstly time complexity and space complexity. We mainly use linear time for searching for an algorithm, searching for an element in the unsorted array, visiting every element in an array to calculate or something such as, for example, let's say sum of the elements, or updating or modifying elements in array. So now, related on the linear search topic, we can see real exercises from LeetCode, which contains duplicate. This exercise name you can see. LeetCode exercise number 217 contains duplicate. We are given an integer array nums. We need to return true if any value appears at least twice in an array, and return false if every element is distinct. Distinct means it's unique, non-repeatable. Example 1. Input numbers list are included 1, 2, 3, and 1. Output is true. Why? Because the element number 1 like this number 1 occurs at the indexes 0 and 3. It means this one number repeated 2 times. That's why it output true returned. In example 2, if input numbers is equals to 1, 2, 3, 4, output needs to return false. Why? Because all elements are distinct. Example 3, input nums equals to 1, 1, 1, first 3 indexes and other 2 indexes. 3 and 4 also repeated 2 times, 2 also repeated 2 times. We can see 3 times repeated, and output exactly returns true. It's time to solve this problem. Our usual simple structure is, for the solution, we firstly our approach as a mathematical and logical form, and then we just need to convert to the code form. And our usual simple structure We usually call it programming languages as brute force. This approach is compare all of the elements with each other, like we usually do any kind of the element with separately, with operations and iterations. It is simple because we just write simple for loop, but we have a one no side in here. In the example, we have just 4 elements, as we say, which is nums 1, 2, 3, and 1 again. In the example, we have just 4 elements. When we have millions of the elements on the set, our machine would be league. So we need good for time and space complexity solution. To solve this problem in a linear time, we can use hash set structure. What kind of structure is it? This idea is that we don't need to compare every element with every other element, because the requirement is if any valuable, because the requirement is if any valuable appears at twice, we can return true. It doesn't matter we find it in the beginning of the list or end of the list or middle of the list. So we check whether we have already seen in the current number. If we find a duplicate, we can stop just immediately. If no any duplicate is found, the algorithm checks all elements in the worst case and then return false. So mathematical step, we can see firstly, what should we do? Firstly, we need to create hash set. It means new like this set to collecting the elements for the comparison, and then loop through every element in an array to checking. And the third one, if the current number is already in the set, we just need to return true. And the fourth operation, otherwise, it means if there is no any kind of the element inside the set, we just need to add from list to the hash set. And finally, if the loop finishes without any finding the duplicate, we just need to return false. So we can see the solution mathematically. We have a nums again, a list 1, 2, 3, and again 1. And firstly, we need to calculate the length, which is we have how many elements we have 1, 2, 3, 4. It means n equals to 4. This is the length of our array, and we just need to put one variable with set to collect and compare with each other. So first iteration, what should we do? This is the first iteration. Num we can get from zero's index or first element. First our element is 1. In set we should do firstly, we put inside the set because our set is blank, and then it returns false inside the loop because there is no any kind of the duplicate or repeated element, and then our set returns collects it. And second iteration, we get the second element, which is 2, and we check it. If there is any kind of the element which is number 2 in the set, answer is no, it means false, no. Then it insert the element 1 and 2 after that. And third iteration, we can see again the next element is 3. We are checking from our set, which is no, answer is, and then it also inserted. Fourth iteration, we can see number which is 1. We are checking. We have already 1, 2, 3 these elements. This element is repeated in that set. Answer is yes. That means true. it responds, and operation will stop here, and our final return is show it true. That's it. Now we can just convert its code solution format. We have a class and we have a function nums list we have, and it returns boolean format. We can write in here. Firstly, we need to put one variable which is seen, and data type is set. We can write just one loop which is num in this from the list of the array. If num is in the set, yes, the set's name is seen, just return true. That's all. Otherwise, this is a exclude of the if solution, if condition. Seen needs to add the num, yes, and then after, otherwise, if there is no any kind of the duplicate elements which is not repeatable or distinct, it just return false. So we can see the test result. All of the cases are worked and accepted. Our next topic is constant time, which is one of the easiest and shortest and sometimes fastest topic in the algorithm and the data structures, complexities. It is also called big O of n. This means that no matter how large its input becomes, the algorithm always performs the same number of operations. Its running time doesn't change as input size grows. If we draw this graph, it looks like this. This is, let's say, the memory or space. If you compare it with space complexity and the input size, or time complexity with input size, doesn't matter. It shows, for example, let's see if you see the vertically O of 1 showed like this shape. It's not any linear growth, it's not any change dramatically or gradually. It only shows only one constant time. So as I said, no matter how much the input size increases or decreases, it always uses the same amount of the time and space complexity. A simple real coding example is accessing just the first or last element of an array. We can see that, for example, we have a nums, which is 1, 2, 3, and etc. 100. If we just calculate and get it nums just 0 element, it automatically comes the first element. First, yes, 0's index, first element it comes. Or let's say minus 1. Anyways, any kind of anyways, how many elements we have in this array, it directly gets from the last element. So it was a very short and understandable topic in the complexity. The next complexity type is square root time. O of square root in n, we can write. The running time of the algorithm grows proportionally to the square root of the input size. In other words, if input is n, the algorithm performs about the square root of n operations in the worst case. Like if our input size is 16, that means our time complexity becomes just a 4 after the square root of the 16. And if our input size is 100, it becomes 10, and etc. Because of this, square n is much faster than the on, like the linear search, when it compares their functions as well. We can see this is a linear function. This is a linear time, if we see, as we drew before, and this is a linear. This is a square root time. Square root time. It means this is much more faster than it. And if we continue to check with these square roots, if we see that, let's see that 10,000, and it becomes 100. Look, This is an input size 16 and output is 4. We compare. It's a simple example. If our input size is 100, it's not became 100, it's just became 10. If we compare it with the linear growth, it had to become, or it could be became 100 as well. And if our input is 10,000 and output is performance only 100. This is the main difference between. So what kind of common problems that can solve with this square root time complexity? Mostly, just as a simple example, we can check whether number is prime or complex, square root decomposition algorithms, and etc. We can see one of the example of the problem which is this simple example problem. That we're given determine whether n equals to, which is input equals to 36, is a prime or composite number by searching for its divisors. How many steps are enough? How many steps are enough? It's asking to find divisor of 36. So firstly, we need to find this input size, input numbers divisors, and then we need to return steps, which is to find divisors of that input size. We can see what is a prime and what is a composite number. So prime number is when zero is divisible. So the prime number is actually when 0 is divisible only 1 and only itself number, composite number. This is a prime number. So prime number is 0 is divisible only 1, or that input size number itself represents. And composite number is divisible by 2 or more numbers, not only 1 and itself, but also the other numbers. Like for instance, 36 can divisible, let's say 1 and itself, and 2, 3, 12, 4, 9. It means this number is composite, not prime. If we see the 7, let's say, or just the 37, it only can divisible 1 and 37 itself, no other any kind of the numbers. That's why this is a prime number. So determining whether number is prime or composite starts checking from, like, let's see, the 2 up to 1 number less than the given number. If none of the numbers divides it, the number is prime, as I said. If at least one number divided it, except from the itself and the 1, the number is composite. So let's see the mathematical form. As we say, input is 36 as given parts given parts represents. We can see its divisions, which are 1, 2, 3, 4, 6 as well. We have 9, 12, and then 36. It means 36 is composite number. So as input size grows, the number of the operations also grows, as we know. So is there any more optimal solution we have, except from checking all of the elements in the divisible in that number? Because our question is not return all of the divisors, but only steps. How many steps are enough to find that divisor, which is prime is this number, or composite is this number? The rule is clear, no? But again, the same question: do we really need to check entire range of the elements in the list? Answer is no. We don't have to check it. We can check easily the 1 or that numbers itself and other elements. If any other elements except from itself and the 1, we can just write down immediately this is a composite. Otherwise it's a prime. That's it. So let's write 36 as pair of the factors, which are, let's say, what kind of the numbers multiplication becomes a 36. Like firstly 2 multiplied by 18 is 36. 3 multiplied by 12 also. 4 by 9 as well. 6 by 6 as well, and then again 9 by 4, 12 by 3, and etc. All of the multiplication pairs are equals to 36. So if we see carefully and notice that after 6 by 6 these pairs are repeated, that it means the same pairs in the reverse order. This pattern works for any number if we see the other examples as well. Therefore, instead of checking every possible divisor, it is enough to check only up to square root of the number, Yes. So another solution or another example, let's see, for example, our input is 37. It only can calculate, there are not any pairs, it means. Yes, they have, if we calculate this with pair solution, we are just following it. 6 by 6 is 36 plus 1, and then it becomes the 37. If we add any kind of a number, that means if we add, any kind of a number after the multiplication, then it means this is also the prime number, we can call it. So if we follow the structure, this approach, we can see, firstly, we need to convert its square root, which is 6, and then 6 modulo by firstly 2, it means, yes, it is divisible. And then 36 modulo by 3, it's also yes. 36 till modulo by 6, also yes, divisible. We only check it up 6, and almost all of the elements are divisible, enough to divisible. That means we can just calculate these steps, how many steps it reached. Another example is 37, we can see, for the prime number. This is a composite number, as we said. The square root, approximate square root actually, is also 6. We check only these steps, which are again 37 modulo by 2. Is it eligible? Is it divisible or not? Answer is not. So we can continue. 37 modulo by 3, it's also not. Till 37 divisible modulo by 6, it's also not divisible. As we said, we only checked up to 6, and none of the numbers divided 37. It means 37 is prime number. It is divisible only 1 and 37 itself. Okay, we structure the mathematical solution. So again, the rule is to determine whether number is prime or composite. First check whether that element of the divisor pairs is less than or equals to that number. And then therefore it is enough to test divisibility only up to that square of the n. If divisor is found, the number is composite. Any kind of divisor is found, number is composite. If no divisor is found, the number is prime. So we can just convert the code solution. So we have a function which is prime, and we have integer data format which is input n. First we need to check it whether it is less than 1 or not. If this input size is less than 1 or equals to 1, we just need to return false, which is it is a prime, non-prime, or non-prime or non-composite number as well. This is the first checking point. And then firstly we need to set that divisor is equals to 2 actually, because 2 means the smallest potential divisor of a number, of any number. Since every number is divisible by just 1, checking 1 is useless. That's why. So that's why we can write the divisor is equals 2. And then while that divisor multiply again divisor, which is the square root time, is less or equals with that input size, and we write the condition if that n multiply or the modulo by divisor which is it returns the remainder part of the result exactly equals to 0, which is it is divisible, and then it returns false. False means the just number is composite. Otherwise, divisor, we need to just calculate its steps, how many steps it performs. Divisor plus n equals to 1. And otherwise, we can just return true, which is number is prime. So if we call our class and our function, which is print solution dot our function's name and then its argument, which is let's check with firstly the 36 and then 37. Run it, finish it, and return false. False means it is a composite number. And if we check it 37, we check it and return true. We can see another like the mathematical example with the iterations, which let's imagine we have an input number is 29. So firstly we check 29 is greater or less than 1. It is greater than 1. We can continue. So our first iteration is we can say the step is divisor is equals to 2. That means 2 multiplied by 2 equals greater or less than 29. It is, yes, less than 29. That means true. So, and then 29 modulo by 2 is equals to 0. Answer is no. It is not non-divisible with the 2. So, and then divisor is increased to 3. That means that 2 divisor is plus n equals to 1. And then second iteration we can say divisor is 3, and then 3 multiplied by 3 equals to 29, which is, this is also true because 29 is greater than the 9, multiplication of the 3 by 3. And then 29 modulo by 3 is also, this modulo is exactly equals to 0. Answer is no. Then we can again the divisor plus equals to 1, that after that becomes 4. Then our divisor is equals to 4, and again 4 by 4 is greater or equals to 29. No, still 29 is greater, which is we can continue, and 29 modulo by 4 is also exactly equals to 0. Answer is no. Again it increased 4 plus 1, which is 5, and divisor equals to 5. Again 5 multiplied by 5 is greater or equals to 29. No, 29 is still greater than, and 29 modulo by 5 is exactly equals to 0. No, which is 5 plus again 1 and 6. It becomes divisor is again 6. 6 by 6, 29 is yes or not. That is 36 is not equals to or not greater than 29, which is false. It is just we can see we can stop our loop in this operation, in this iteration, which is our steps are 6. We can see. So to loop, the loop finishes and no any divisors were found. The code returns true, which is this 29 is prime number. If any kind of the result appears in here that modulo is exactly equals to true, exact is equals to the modulo is exactly equals to 0, then we can say yes, this is a not prime, this is a composite number, because this is divisible except from 1 and itself. So our next topic is quadratic time. Quadratic time, as the name suggests, means that as input size increase, the execution time grows gradually. For For example, if the number of the elements increases 2 times, the processing time increases 4 times. Like if our input size is 2, then output becomes 2 squared by 2 is equal to 2 over 2 is equals to 4. If our input size is 10, then it becomes 100, and etc. Because of this, the algorithm becomes much slower as input grows. It's a simple explanation. Why do we need to understand that quadratic time? There is two main approaches and answers. Firstly, finding any anti-patterns. It helps us identify approaches that may cause any kind of the lags or freeze when working with a large amount of the data, especially not ordered but disordered data as well. Sometimes we will also face with it. And then optimization we need. That means it helps us compare solutions and determine which one is more efficient, such as big O of n squared, quadratic, or big O of n, or big O of logarithmic n, we will see, and etc. If we see that function with linearly, its shape looks like this, quadratic time. If we have an input size and time complexity, we can compare. So as we talked before, if you follow one of the simple concept, firstly with any kind of the problem to solve that, which is called, as I say, the brute force. That means starting with the just simplest and more straightforward and correct solution that first comes to mind for solution, solving the problem. After that, we can use this solution as baseline firstly, and then optimize this step by step. This is a baseline we usually call it, as a simple example, brute force. So quadratic time is commonly used with algorithms that compare the elements in an array, such as like the bubble sort, one of the popular one, insertion, selection or insertion sorts. So that one is the explanation, and there are real examples. We can see some problems with exercises. So we are given an array of integers, which is called nums, an integer target. This is 2 inputs, and we need to return indexes of the 2 numbers such that they add up to target. That means, example 1, we can see input is when nums equals to 2, 7, 11, and 15. Target is 9. That means output is 0 and 1. Why? Because number of the zeros index plus number of the first index sum is equals to 9. That means 2 plus 7 is equals to 1. And we can just return 0 and 1. Another example, 3, 2, and 4, when the array and target is 6, we can just return 1 and 2 index, which is 0, 1, 2. 2 plus 4 is equals to 6. If we couldn't find any kind of the number to target, the sum of these elements is equals to target, we can just return the false. You may assume that each input would have exactly one solution, and you may not use the same element twice. Yes, we don't have to use. We can't use the same elements with itself or with same elements again repeatedly. Solution. Usually firstly mathematical, then the coding solutions from high level to low level. So high level process is, what should we do? We have a numbers which is 2, 5, 11, and 15. I think the 7 is, yes. When target is 9, 2 plus 7, then it becomes 9, yes. So we need to pick the one element from that set, that array. We can call it just the I, index the variable, and we need to compare it every other elements after the index I. Like we can call it J, for example, after that other elements. This is a separate element that we pick it up, and others are the separate elements or separate sets, we can call it. And then when that numbers I element plus that G element is exactly equals to the target, then we can just return these 2 indexes. So otherwise we can just return the false. This is a main high level process. So low-level solution, when that I is equals to 0, the G loop checks n minus 1's element, because we cannot pair an element with itself. That we have, let's say, this 2, we cannot check the 2 and 2, only 2 by 7 and 11 and 15. If we pick it up, if we pick out the 7, we only check it up the next numbers, 7 plus 11, 7 plus 15, that's it. If we pick the 11 only check with the 15. If we pick the 15, we don't have to check with any elements, because before that we already checked it. Like 15 plus 2, 2 plus 15 are the same. And third one, we continue the process until the last element. This is a simple, like the mathematical, like the also formula also represents, which is arithmetic progress, n minus 1, like plus then n minus 2, and etc, 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 and the last one is just equals to 1. That arithmetic progress formula is, we can see the as in the mathematics as a1 and a(n)'s element divided by 2 multiplied by n of the element, number of the elements. In our case, the first our item is 1, as we see, because any kind of the element starts with n. It starts with 1, which is the index number, because the sequence adds and 1 at 1, like this. And total number of the elements, as we said, n minus 1, because we don't need to, as I said, giving the twice, like the duplicate numbers. The formula becomes like this: a1 is equals to 1 in our case, and an equals to n minus 1. Like a is equals to 1 plus n minus 1. We're just proving the mathematical form in the formula. Multiplied by n minus 1, and then if we calculate them, n quadratic by 2 over 2, n over 2, n by 2. So ignoring the constraints and the lower order terms in the big O notation, we can see n quadratic over 2 minus n over 2. We just ignore it because this is one of the highest, the square root. This is the highest root. That's why we just pick only that square, which is O(n) square. This proves why algorithm has quadratic time complexity. So now let's see the progress. We have again the n equals to 2, 7, 11, and 15, and target is 9. First, our loop is I equals to 0's element, which is 2, and j's element is I plus 1, which means the next element, the second element, which is 7. If we sum them, that exactly equals to 9. Yes, this is exactly equals to 9 if you also wrote the if case, the condition case. And let's end up with all of the operations, which are I equals to 0 again, which is we need to first let the finish the first index to other indexes, plus again j equals to I plus 2, which is 11. It also becomes the exactly equals to 9 or not. No, I equals to 0 again, 2 plus j plus I 3, which is 15. This is also not exact with 9. And we finished the first loop. We can check the second loop as well, which is I equals to 1, the next element, the next index, which is the 7, and plus j plus that element I plus 1, which is the second element, 1, 0, 1, 2, second index. This is also, 11. This is 18, which is not exactly equals to 9. Again, I equals to 1, which is 7, plus j is equals to I plus 2, which is 13, 15. This is also not exact with 9. And the third loop, we have I equals to 7, which is 11, plus j plus I plus 1, which is the third index we need to pick. And this is also not exact with 9. And last for loop, we can see I index equals to 3 because this is the last element. 15 I plus j is equals to I plus 1, which is a 4. 4 means our last element. This is also, we don't have any element. 0, 1, 2, 3. So range is 4 of 4. That's why we just finish our loop. This is the last condition, we can say. So it's time to convert just the coding solution. We wrote all of the process. So we have a function which is a toSum, nums which is a list format, and target which is integer format. We need to return the list format as well. So what should we do? Firstly, we need to just write one variable, which is we need to firstly calculate get length of the input array, which is nums, because we need to range as well. So and then we write the outer loop for I in range with n, which is our input size of the list. So we need this loop because we need to pick one element at a time. And again, we can write with the g in the range again with I plus 1, as we see. That's the first element, and the last range is we can write the n, which is we can call our inner loop. This is outer loop. So what's the difference between them? Input loop compare the current element with all remaining elements. And we start from the I plus 1 to avoid comparing an element with itself. And avoid checking the duplicate pairs as well, as we say 2 plus 9, 2 plus 7, also again 7 plus 2, it's useless. That's why we need inner loop as well. So after picking up these two comparison elements, we just write down if nums that I index plus nums j index is exact equals to target, yes, then it can returns that exact I and j element. Otherwise, we can return just blank. And any other cases, this is outside of the inner and outer loop as well, we can just return the blank of the list. If you check the test result, we can see all of the cases are worked and performed well. Output is 0 and 1. That case output 1 is 2, and that case 0 and 1 again. This is a main case of the quadratic time complexity. So the next topic is logarithmic time. So logarithmic time means the input size becomes smaller by fixed ratio in every iteration. So instead of checking every element one by one, the algorithm repeatedly eliminates a large portion of the remaining data. Because of this, all logarithmic n is, we can see logarithmic of n is considered one of the most efficient time complexities. We can say if we draw its functional representation, we can see the input size again and the time complexity. Its line looks like this shape, logarithmic shape, because it increases gradually as input size increase. For instance, let's see the mathematical form. If our input is n, let's say we can say that n equals to 8, we just compare the converted logarithmic 2 over the 8 to what kind of the numbers the grade is equals to 8, which is 2 over 3. Then we can just convert it, drop it, and then the result equals to the 3. That means input is 8 and output is 3. Again, the next solution, the next example. If our input is greater than the 1000 as well, 1024, and we converted logarithmic 2 baseline with 1024, which is 2 over 10. Yes, we drop them and only 10 results remained, which is our input size is 1024 and output is just 10. Look, this is gradually increasing. So we usually use base 2 when analyzing logarithmic complexity, because many algorithms divide input into 2 equal parts in every step. If algorithm divides the input size by 3, let's say, in each time, then number of the steps based on logarithmic 3 base of n, you can see. This is the main mathematical progress. So let's look at some examples. If our input size is 8, it takes only 3 operations. If our input size is 1024, it takes only 10 operations, not 1024. If the number size is about 1 million, it takes only about, let's say, the maximum 20 operations to reach that answer. This is the main idea behind the binary search as well, which is one of the most common logarithmic algorithms. So, quick real-life example of the binary search we can see. So, exercise time. If we see this real-life simple exercise, problem stated we are given the positive integer, which is n, repeatedly divided by 2 until its integer value becomes 1. Yes, return the number of steps are required. So, let's say we have an integer inputs is 32. First, we need to check it. 32 is greater than 1 or not? Yes, it's greater. Then we just need to integer diverge with 2, and then it equals to the main, not remainder part, but divisor part is 16. 16, yes. And we need to keep continue repeatedly until the value, integer value, becomes 1. This is the first iteration. And after that, we can pick the remaining part. Divisor part 16, also greater than 1, 16 divisor by 2, 8, and 8 also greater than 1, and 8 divided by 2, it is 4, and 4 is also greater than 1, 4 divided by 2, again 2, and 2 is also greater, 2 multiplied by divided by 2, 1, and the last part is not, we can just stop it. We have 2, 3, 4, 5 iterations. So we just return the 5 iterations, which is steps. And if we calculated logarithmic format, like the converted logarithmic format, logarithm to baseline 32, 32 means, as we know, 2 over 5, which is dropped, and then answer output is also become 5. These are the proof. And if you convert it with the code format, we just write down, this is a function name, which is the divide until 1, and we have input size, which is integer data format, and we just write down steps to calculate them, steps variable, which starts from 0, and we write while loop, and when greater than 1, it needs to be work continually, and we just integer divided by 2, which is n, is exactly equals to the eligible to divide by 2, and return divisor part, and we have a steps, which is needs to sum the plus equals to 1, and we need to return the steps as well. If you write the function name in our argument, which is, let's say, the 32, we can check, print remains. We can see the 5, yes. And if you write this 64, we can see the 6 steps, and etc. LeetCode exercise time related to our topic, which is 704 exercise number. Name is binary search. We are given an array of integers, which is nums, which is sorted by ascending order. Ascending is like this, like increasingly order by order that the filtered. An integer is target. This is a second, like let's say the input. Write a function to search target in nums. If target exists, then return its index. Otherwise, return -1. You must write an algorithm with all logarithmic and runtime complexity. if our input is nums equals to -1, 0, and etc. till 12, target is 9, input needs to return the 4. Why? Because 9 exists in nums. Yes, 9 exists in the nums element, nums array, and its index is 4 because 0, 1, 2, 3, 4. We need to return its index. So example 2, if our number is equals to 0, -1 like these elements, and our target 2, output -1. Why? Because 2 doesn't exist in the nums, so we just need to return -1. So question is understandable. We can see firstly the main idea behind it, about the binary search. So let's imagine we have the dictionary book which 1,000,000 pages, and if we want to find the word, for example, that name it system, we have a big, let's say, book with 1,000,000 pages. So method 1, start from the first page. We need to check every page, until we found the words. This requires checking up to 1,000,000 pages. This is a much more slower and much more useless. Not actually useless. Is useless than other, like the better solution. If you follow that's approach, which is a simple linear search, we can find maybe until 1,000,000 pages we need to find, we need to check. The method 2, we just open the dictionary in the middle side. Let's say, for example, that middle page starts with words with M, let's say. Since the system comes after M, systems as words comes after the M, we can immediately ignore the first half like this, and we can keep continuing the next halves, and then again open the remaining section in the middle and repeat the process. At every step, almost half of the remaining search space is eliminated. This gives us the following relationship, which is n equals 2 over k, which is k is equals to logarithmic to baseline n. We can say this is exactly binary search is, such an efficient searching algorithm. The only main requirement is the array needs to be sorted. This is the main, just a simple requirement. So the solution of the first exercise, we can see the first step from the high level. We need to take the middle element of the nums array and compare it with the target. If the target is greater than middle element, we just go to the right half. If the target is smaller than the element, we just continue to searching the left half and ignore other half, and we can repeat the same process until the target is found or no elements remain. We can take the examples from the LeetCode's array, which is nums -1, 0, 3, 5, 9 and 11, 9 and 12. Target is 9, and output needs to be force index. So we can separate them, which are, this is a left side and this is a very right side. And middle's formula is just the left plus right divided by 2. Divided means integer division. So we can see the minus, like this index number we can get, not actually that element, which is 0, 1, 2, 3, 4, 5, plus 5, and divided by 2, the divisor part is 2. That means we nums 2's index, we need to convert it element format 0, 1, 2, which is 3. 3, we can see, is greater or less than, smaller than the 9. This is a smaller. That means we need to go to the right side. We just need to ignore the other sides, which means we can just ignore that side, even the 3 as well. So in the remaining part we can see 0, 1, 2, 0, 1, 2, 3, 4, 5. We can start from the third index. That means our second iteration is, we just left is equals to like middle plus 1. Means target doesn't need to equals to that middle, the part, that's why. So that means that part is, or we can write the right part, right side, which is 3 plus 1 is 4. Fourth index we need to start like this. From 5 we can see. And right plus left again divided by 2, which are 3. Sorry, this is the second index and it becomes third index. Yes, third plus the last element is 4, 5, 5, 3, 4, 5, and 3 plus 5, the right side's element, divided by 2, it equals to fourth element. If we check that element, which is the fourth element, 0, 1, 2, 3, 4, which is the 9, is exactly equals to 9? Yes. We just need to stop in here the process, the loop, and this is second iteration, and return that middle of the elements index. This is a simple mathematical form you can see, and we can easily convert it, go to solution. We have a function inside that arguments have the nums list and target integer. We need to write firstly left side, which starts from the 0, because this is the index, starts from 0's index, and right side is equals to len nums, firstly len of our list numbers, and minus 1. Why? Because for the right side take the last index based on the range. Range, as we know, if our range is like 4, that means it returns the 3. That's why we need to write the minus 1 as well. So, and where we write, it needs to be stopped while left side is less than the right side, which is the right side needs to be greater or equals to right side, left side. Searching while there are still elements to check, that's why. And then we need to write the formula, which is middle is equals to left plus right side, and then integer divisor by 2. If the middle element is that target, we just need to return that. We need to find the middle of the index of current search page, that's why. And if that nums middle index is exactly equals to target, we just need to return mid. Other case, which is LE, we can write nums that middle index is less than target, we just go left or right. This is the main condition, which are if our middle element is smaller than the target, search on the we need to search only the right half. That's why we can write left is equals to middle plus 1. And else, at other cases, we just write the right cases, which are middle plus 1. Sorry, middle minus 1, because it needs to go that opposite direction. And any other cases, we just need to return minus 1. That's basically it, yes. If you check it, we can see, yes, our two cases also worked properly. The next complexity type is exponential time. That means that every time the input size increases by 1, the number of the operations and therefore the running time doubles. That means 2 over that 1. So, in the simple terms, it is the opposite of the binary search, we say. Instead of reducing the search space by half, opposite, the number of the possible cases doubles at every step. That is why it's called the exponential time. Let's say we can see the 2 over the 2 of 1 is input, the output is 2. That 2 over 2 is equals to that 4, like that means the input size is 2, output becomes 4. Our input size is not actually the 5, that means 2 over 5 is equals to 32, let's say. This is the main idea behind of the exponential time. So this complexity usually appears in recursive algorithms where at each step we make two choices, such as take it, that element, or leave it, that element. Some problems cannot solve without checking every possible cases. That cases we need exponential time, which is, let's for example suppose we are given the integer n, and our task is to generate all possible, like let's say binary, the bits of strings length of n. For instance, we have n equals 2, the input is like 0, 0, the 2 bits. The possible outputs we need to the return, like 0 and 0, 0 and 1, 1 and 0 based on its bits, and 0, the 1 and 1. That means how many elements we have? 4 elements. Another example, we have the, let's say, 4 possible combinations. That means we have 4 possible combinations. Since each bit has 2 choices, 0 or 1, the total number of combinations is equals to 4, that's why. So if our number inputs is equals to 3, the output becomes like this. If we converted binary search bit format 0, 0, 0, 0, 0, 1, and 0, 1, 0, we can write 0, 1, 1, 1, 0, 0, what else? 1, 1, 0, again the combination 1, 0, 1 and 3 ones. If we measure them, if we calculate them, these 8 possible combinations we have, because of 2 over 3 also becomes 8. At each level, every bit has 2 choices, choose 0 or choose 1. This shapes also looks like this, with these possible combinations. It splits like yes or not, looks like this. Each decision creates, this is also a decision tree we can say, and we can call it. Each decision tree has 2 new branches, so the total number of possible combinations doubles at every level. That's why the total number of output is 2 over the n, exponential time. So exercise time we can see, which is exercise number 78, named subsets in the LeetCode. This is a little bit medium level of the exercises. So we are given an integer array, which is nums, of unique elements. That means these things. Return all possible subsets, that power sets. Their solution set must not contain duplicate sets. Return the solution in any order. Like if our input is nums equals to 1, 2, 3, we need to return the firstly blank, the combination, and then 1 separately, 2 separately, and then starts 1, 2, 3 separately, 1, 3, 2, 3, 1, 2, 3, like these combinations. If our number input is equals to 0 in the set, in the array, we just need to return the blank element and just a separate 0, that number element. So notice that we have 3 elements. We can see the first example, which are 1, 2, and 3. For each element, we always have 2 choices, which are include that element or exclude that element. Decision for element 1, let's say we can see in the decision tree, 1, 2, and 3. We have a 1, let's say, and we take it or not. If we take it, like the 1 is yes or 1 is no. If we take it, that our element is in the set becomes 1. If we say no, that is just a blank element. Again, we will keep continuing for that. If then we can decide for 2, like exclude 2 or include 2, like 2 is yes for yes or 2 not. If we decide yes, then 1 and 2 it becomes. If we decide no, just the 1, we just write left only 1. So no cases we can say. If for 2 is yes or 2 not, if we say yes, then our inside the element becomes 2, and then no, there's still blank. We don't need to write 0. And then again 1 and 2 case, we have the next element is which is 3 yes or 3 no. If we decide yes, we can write 1, 2 and 3, and if we decide no, we just keep it 1 and 2. For the next case as well, for the no case, which is 3 yes, 3 no. If we decide yes, 1 and 3 we can write. If we decide no, just 1 we keep. For 2's case, if you write 3 no, 2 just to keep. If we decide yes, 2 and 3 we can write down. And the no's case, if it's 3 no, we just need to keep it just a blank set of array. If it's 3 decide yes, just we can write 3. And how many operations and combinations we have? 1, 2, 3, 2, 3, 4, 5, 6, 7, 8. 8 operations. We just need to return all of these combinations like this. So based on these operations, we can see since every element has 2 choices, like yes or no, the total number of possible subsets are 8. We can see leaf like the elements. So based on the 2 over 2, 2 by 2 and 2 multiplication. In a general, for any array with the n elements, the total number of subsets are 2 over n exponential time. Through this process, we temporarily store subsets in the past and collect them later like this. This process is called, we can see, the backtracking. We can just convert this mathematical logic form to code format. So we have a class solution, we have a subsets which are numbers, list, integer with the integer formats, and another lists. We can see the output needs to be returned the list format. So first off, we need to write the result for the list, empty list, for collecting the final subsets. And we need to write again the separate backtrack named the function for create a recursive function. Like we can see the index, which is integer format, and we have a path, which is a temporary result, which is a list of integer. It needs to be returned. So index shows which element are currently making the decision about. Like path also stores the element is selected for current subset. We can see, yes, current that subset. And then after all, we can write down in the results, inside the results list. So we can write the condition if index is exactly equals to length of the numbers, yes, which is a base case. So when index reaches the end of the list, the current subset is like the complete, like a result, just append path, and we can return it. That's it. So this is a base case, and we can write the decision 1, which is the backtrack, our function's name we can call it, and we can write index plus 1. Why? Because we exclude the current element, and it starts from the first indexed the element till path. We can check it. And decision true for the include decision we can write down. Again, backtrack function, index plus 1 again, and path with plus nums index as well. Why? Because that include current elements create new list for adding nums index to path. The original path remains unchanged. And we need to call again our function's name for the start the recursion, which is index needs to start from 0 and blank set of array. We need to write it outside of the function, and we can write return result. If we check it, we can see all of the cases are worked and worked properly. So one of the last complexity type that we are seeing is factorial time. Factorial time appears when at each next position we just choose one element from the remaining elements. The number of the choices decided like this: n minus 1, n minus 2, and etc. until the 1. Therefore, the total number of the combinations is n factorial, which is calculated using factorial formula, as we say, the mathematical form, the n multiplied by n minus 1, again multiplied by n minus n over, again multiplied by n minus 2, and etc. till 2 and multiplied by 1. In programming, this complexity usually appears when generating and checking all appears possible, like the permutations we can call it, meaning all possible orders of elements. Like we can see, if our n is equals to 1, that means 1 factorial, that means 1 operation. If n equals to 3, that means 3 factorial, means 3 multiply 2 multiply 1, that equals 6 operations. Again, if our n input equals to 5, 4, 3, 2, and 1, it equals to 120 operations. A computer may needs, like if we write down in here the 20, that 20 factorial becomes some kind of the big numbers. A computer may need years to calculate them all. Why we use it, this factorial time? It is mainly used for permutation problems, as I said. We will see the real examples, such as finding all possible ways to arrange n items in a row. And it also appears in brute force attacks, such as checking all possible arrangements of password check, like the characters without repetition, such kind of that problems or tasks we can use. So practical exercise time. So we can solve exercise number 178 from LeetCode, which name is factorial trailing zeros. We are given an integer n, return the number of trailing zeros in n factorial. Note that n factorial is, as we saw, n multiplied by n minus 1, n minus 2, and etc. to multiply 1 with n's. Example 1, if our input is n equals to 3, output needs to 0. Why? Because factorial 3 is equals to 6 zeros, no trailing 0. Example 2, if our input is n equals to 5, output needs to be 1. Why? Because explanation is 5, the factorial is equals to 120, 1 trailing 0. That means it ends with 1 0. The next example, if our input is n equals 2, our output also needs to be 0. So we can see a straightforward solution would be first compute n factorial. However, the problem is only asking for a number of trailing zeros, we can see, not as a factorial itself. So for small values of n, calculating the factorial is not a problem, but for large values it can easily cause integer overflow, becomes unnecessarily expensive. That's why we don't have to calculate all of the possible permutations, all of the multiplication of the n factorial. We need to find the other better solution. So let's move it from the different perspective. A trailing 0 appears whenever the number is multiplied by 10, no? Or other cases like 2 multiplied by 5 or 4 multiplied by 5, these cases we can see. Since 10 is equals to 10 over 10, 10 is equals to 2 multiplied by 5, every trailing 0 is formed by one pair of 2 multiplied by 5. We can calculate. In factorial, there are always more factors of 2 than factor of 5. Therefore, the number of trailing zeros depends only on how many factors of 5 appears in. So we just need to focus on the 5, the number of the 5. examples we can see as the LeetCode gives us before, which is we can see that n equals to 5, let's say, input, which is, as we know, 1, 2, 3, 4, and 5 we have. There is one factor of 5, so there is one trailing 0. Let's say the input is 10 factorial, it becomes 1, 2, 3, 5, and etc. till 10. The multiplies of 5s are like 1 and 2. That means 10 equals to 2 multiplied by 5. There are two factors of 5. There are two factors of 5. That means we have two trailing zeros. We can decide. So general formula, if we convert it to mathematical formula form, we can write trailing zeros and divide by 5, and we can get it the divisor format, plus again n divided by 25, which is a 5's the second grade, again, and 125, and etc. It depends on our size of our inputs. So this works because the n divided by 5 counts all multiplies of 5, and divided by 25 counts extra factors 5 contributed by multiply by 5, multiply by 25, and etc. Let's see with, for example, some kind of the input. When our input is 26, let's say, our first contribution is 26 multiplied by 5, and its divisor part becomes 5. And then again we can divide by 25 because it is 26 is greater than 25. That's why we need to keep continue it, and it returns 1 because 25 multiplied by 1, and then we can add some kind of a number. We need just the divisor, the part of the number. That's why. So, and then if we divide by 125, if we keep continuing, it cannot divide because the divisor part becomes 0. That's why we can stop in here. Therefore, we have a 5 and we have 1. We can just sum them. 5 plus 1 is equals to 6. That means, so 26 the factorial is equals to 6 trailing zeros. We can decide. So we can just convert it the code solution format, and we can see the result. We have a function name, we have an input which is an integer format. So we need to write variable named count which is equals to 0. It stores the total number of the trailing zeros. That's why we write down this equals to 0, and the loop is continue until there is no more multiplication of the 5. That's why we can write down in here n greater than 0. And count, we need to count how many numbers are divisible by 5 and 25 and 125, like this. That's why we need to write and the integer division equals to 5. And we need to add current count of factors of 5. Count plus is equals to n, that's it. And we need to return our count of the steps. If we see the results, we can see in here all of the test cases are worked. If n equals to 3, output will be 0. If our input is equals 5 factorial, output becomes 1. And if our input is 0, output also becomes 0. So summarization, let's summarize the difference between all of the most common time complexities that we learned before. So in conclusion, O of 1, which is a constant time, number of the operations remain same regardless of how large input size becomes. If we represent all of them in the functional format, we can write down in here input size in here we can represent, and computations. Constant is maximum, we can see in here, representing here maximum closer to the 0. It's much more better. And all logarithmic time algorithm repeatedly eliminated large portion of the search space at each step, and such as a binary search, we can represent it like this shape. We can see one constant time, and the next one is square root time. We saw instead of the checking up to n, algorithm only checks up to square of the root, which is commonly used for problems such as prime number or testing. We saw the quadratic time. The algorithm compares each element with other elements, making it common pair comparison problems and simple sorting algorithm, such like the bubble sort or insertion sort we will see the next. And like this shape, and exponential time is also looks like these shapes based on hour. We can filter them as like complexity function lines. So to conclude, complexity helps us understand how algorithms running time and memory usage how grows as input size increases. So when solving a problem, we should always ask how many operations does this solution perform and how much extra memory or space does it use, and can we make it more efficient. Understanding the complexity help us compare solutions, recognize inefficient approaches, and choose algorithms that can handle large amounts of data. Thank you very much for attention.